Hello geometry students, and welcome back to another video. So what we do at the beginning of each video is there is a problem on the screen from last video, and what you're going to do is you're going to pause this video and try this problem in your notes, and then when you're done trying it in your own notes, you're going to unpause it and do it with me. So do that now, pause the video and try it in your own notes. Now unpause it and let's work together. So the first thing we're going to do is give another name for segment KL. That's how we read this. We read it segment KL. The reason I know it's a segment and not a line is because it doesn't have these arrows. If this had those arrows, it would be line KL, but it doesn't have arrows. It's just a little stick. So that is a segment. There are only two ways to name a segment. Segment KL. So both ways to name segments require using the endpoints of that segment. Now I can say segment KL just like this, or I can say segment LK, because if I pick this segment up and I flip it around, it is the exact same thing. Whether it is LK or KL, it's the exact same thing. So, another name for segment KL is segment LK. Different color. Let's look at the second question. Are KP and PK the same ray? Okay, I need to draw. So the first thing I'm going to do is I'm going to find these rays on my diagram. So KP is this ray. It starts at K and it points away from it. And actually I'm going to do PK in a different color so we can see. So now I'll do ray PK that starts here and it points towards K forever in that direction. So are these the same ray? Is the yellow ray the same as the green ray? Well, no. No. KP and PK are not the same. Because they have different endpoints. Because they have different endpoints. Okay, so now let's erase our diagram and make room for the second part of this question. Our NP, so let's see, NP is this ray, and it goes on forever, so we could draw it like this. It goes on forever in that direction. Alright, so is NP and NM the same ray? Explain. Ooh, so yes. Yes. Ray NP and ray NM are the same. Because they have the same endpoint. Ah, same endpoint. Perfect. You can read that. So the difference between ray KP and PK was they were pointing in different directions. They didn't have the same endpoint. Now, if they had said PM, if they had asked if NP was the same as PM, then the answer would be no, because they don't, even though they're pointing in the same direction, they have different endpoints. But because NP and NM have the same endpoint and are pointing in the same direction, they are the same. Well, there you have it. Were you right? Did you get the problem right? If so, good job, and if you didn't, that's okay. Maybe you want to re-watch last week's video. Maybe you want to ask your teacher for clarification. This problem is just a check to make sure that you understand what happened in last week's, or not last week's, excuse me, the last video, to make sure that you're ready for this video. Speaking of this video, here's what we'll be talking about in this video. We are starting section 1.2 today, and 1.2 is all about measuring and constructing segments. So, the learning target for this video is that you know how to measure segments, you know what makes segments congruent, and how to compare two segments. And how do you know if you have met that learning target? Well, you will be able to use the Ruler Postulate, you'll be able to find congruent segments, and you'll be able to use the Segment Addition Postulate. So both of these are very important, and I look forward to telling you all about them. So, first thing we're going to learn about is the Ruler Postulate. You have probably seen this before, just with a different name, and if you haven't seen it before, that's okay, you're seeing it now. So what this says is that the points on a line can be matched one-to-one with real numbers, because there are infinitely many real numbers, and you can make infinitely many points on a line. The real number that corresponds to a point is the coordinate of that point. And you've seen coordinates on graphs before. That's where we have A is 1, 2. It means that point A is at these coordinates. All right, and the distance between points A and B, written as AB, is the absolute value of the difference of the coordinates of A and B. That's a mouthful. What it means is you take one coordinate minus the other coordinate, and you put absolute value around it. It doesn't matter if you do x1 minus x2, the absolute value makes it the same. So, distance between two points is the absolute value of the difference. That's the most important thing to take away from this Ruler Postulate. We're going to see two examples of the Ruler Postulate. The first, I thought, was a little silly the first time I saw it. Like, why is the ruler over here? Why don't you just put the beginning of the ruler where S is? And I was talking to my husband about this. This example is dumb. Why would they do this? And he said, well, I've measured things before, or other people have measured things for me, sent me a picture, and then I realized, oh, I wanted them to measure this instead. But you don't have to have them send you a whole nother picture. You can actually use the Ruler Postulate to fix it. So we're going to see this example. We're also going to see another example that I think is a little more helpful than this one, but I also want to show you this one so that you see what the Ruler Postulate looks like in application. So we want to measure the length of ST to the nearest 10th of a centimeter. So these are centimeters. We can tell because it says centimeters on it. So what we're going to do is we're going to match each point with its coordinate. So right here, it looks like S is directly on top of 2. So S is at the coordinate 2. Now, what coordinate is T at? Let's see, T is right above this tick mark right here. And let's see, that's 5.5, right? That's 5.5, and 1/2 is 0.5. So this is 5.1, 2, 3, 4. Okay, so S is at 2, and T is at 5.4. And centimeters, of course. So we know that the distance between 2 points is the absolute value of their difference. So what we're going to do is we're going to do one minus the other. Now you might want to do the bigger one minus the smaller one. You can also do the smaller one minus the bigger one, because we're taking the absolute value of it. And you remember what the absolute value does, don't ya? If you don't, that's okay. So when I do 5.4 minus 2, I get 3.4. Now what the absolute value does is it makes whatever is inside of the absolute value positive. So 3.4 is already positive, which means that this is just 3.4. Now what would have happened if we had done the smaller number minus the bigger number? 2 minus 5.4. Well, 2 minus 5.4 is negative 3.4. But our absolute value makes everything inside of it positive. So this is also 3.4. So see, it doesn't matter whether you do the bigger number minus the smaller number or the smaller number minus the bigger number. As long as you take the absolute value, you get the same answer. So this is our answer. How long is segment ST? Well, it is 3.4 centimeters. And I want to recap how we did that. So we found the coordinates that went with S and T, and then we took the absolute value of the difference of the coordinates. So we subtracted one coordinate from the other, took the absolute value, and we got our length of the segment. So I know this example might have seemed a little bit silly, which is why I want to show you another example. You are going to see things like this throughout the rest of this lesson, so I want to show you how to go about looking at these types of problems. It says, use the ruler postulate to find the length of the segment. So again, we're finding the length of the segment, and we're going to use the ruler postulate to do so. And the way we're going to do this, remember, we take the coordinate of one endpoint and the coordinate of the other endpoint, and we subtract one from the other, and we take the absolute value of that. But here's my question. Up here in this example, S was 2 and T was 5.4. In this example, I have 2, 9 and 2, 3. How am I supposed to know which of these numbers to use? Which of these numbers goes in my absolute value? This is a very good question. So when the line is vertical like this, you can think of putting your ruler vertically. So the y-axis is like our ruler when we're dealing with vertical lines. So the coordinate that goes with this endpoint will be 3. And the coordinate that goes with this endpoint will be 9. And so you can think of, oh, if the line is vertical, use the y-axis, because the y-axis is also vertical. Another way that you can think about this is both of these have a 2 next to it. Both of these coordinates have a 2 in it. So if I use the 2, I'm just going to do 2 minus 2, which is 0. And this segment is 0 units long? Like, no, that doesn't make any sense. So you can't use the 2. You want to use the other number in the coordinate. So that's 2 different ways to think about it. Don't use the one that's the same, use the other one. Or think of it as your ruler is parallel to the axis that your segment is parallel to. That was a lot of big words. Your ruler stands next to your segment. So the ruler will go this way, which means that the y-axis will be your ruler. Whichever way that I just explained helps you think about it, that's what matters. Use that one. So now we have the coordinate of this point is 3, the coordinate of this point is 9. So remember, I can do 3 minus 9, I can do 9 minus 3. It doesn't matter. Both of them give me the same answer. 3 minus 9 is negative 6, and the absolute value of negative 6 is positive 6. Just like 9 minus 3 is 6, absolute value of 6 is 6. So no matter which way you do it, small number minus the big number minus the small number, no matter which way you do it, you get an absolute value of 6, which means that the segment is 6 units long. And that is our answer. Okay, so this is going to help us when we want to know how long each unit is. Now, I know you might be thinking, because I've had students ask me this before, why can't I just count the boxes? 1, 2, 3, 4, 5, 6. There's 6 boxes there. So, you could do it that way. You need to know how to use the ruler postulate for this lesson and future lessons. It's going to come back in 1.4. It's going to come back in 1.3. It's going to come back in chapters after this. So, when it says use the ruler postulate, I want you to use the ruler postulate. If it doesn't say use the ruler postulate, maybe you can count the boxes. But in real life, you won't have boxes to count. So I want you to know how to use the ruler postulate. If it doesn't say to use the ruler postulate, count the boxes. Okay. All right. So, moving on. Now that we know how to find the length of a segment, now we need to know about congruent segments. So, congruent segments are line segments that have the same length, are called congruent segments. You can say the length of AB is equal to the length of CD, or you can say segment AB is congruent to segment CD. This symbol, I'm going to draw it bigger for you. It's an equal sign with a squiggle above it. And this symbol means congruent. Memorize this symbol. You are going to see it in every chapter from here on out. Every chapter. So, memorize that symbol and get comfortable with this symbol. It means is congruent to. So, if you want to say the lengths are equal, you write it this way. You don't need the line above it. You just say AB is equal to CD, and you do not need the lines. You don't need the lines above them. So what this says is this says the lengths are equal. If you want to say the segments are congruent, now you do need the lines, and you need the special squiggly equal sign that means congruent to. So, how do you know that two segments are congruent? They have the same length. If AB is 5 units long and CD is 5 units long, they are congruent. If one is 5 units long and one is 4 units long, they are not congruent. Okay. So, also, these little tick marks mean congruent. Anytime you see a tick mark, and that's what we call these, we call them tick marks, it means that AB and CD are congruent. So, when there is more than one pair of congruent segments, you'll use multiple tick marks. So instead of just having one here and one here, we have 2 here and 2 here, something like that. Also, these tick marks are going to be here for every chapter from here on out. So please, 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 please remember what those tick marks mean. We're going to use them for the rest of the year. Okay, so now, what are congruent segments? Segments that have the same length. Line segments that have the same length are congruent segments. All right, let's use that in example 2, comparing segments for congruence. So the question asks us to plot these points, then determine whether JK and LM are congruent. Okay, I know how to plot points. I'll do that first. After I plot the points, I need to tell whether JK and LM are congruent. How do I know if two segments are congruent? That's right. If they have the same length, they're congruent. Okay, so I need to plot these and then I need to check, are they the same length? If they are the same length, they are congruent. If they're not the same length, they're not congruent. Okay, so first, let's plot these points. J is at -3, 4. K is at 2, 4. L is at 1, 3. And M is at 1, -2. Okay, so I plotted all the points. Oh, whoops, I didn't label them. This is L. This is M. Make sure you label your points so you know what you're looking at. Okay, now determine whether segment JK. So I need to connect the dots between J and K. Now we have a segment. And segment LM. So I need to connect the dots between segments L and M. Determine whether they are congruent. Okay, well, in order to know if they are congruent, I need to know the length. So the length of segment JK is equal to the absolute value of one coordinate minus the other, and the length of LM is the absolute value of one coordinate minus the other. So now we just need to figure out which coordinates to use. So because JK is going horizontally, I'm going to use the ruler that is horizontal. That ruler is the x-axis. So J, and let me use a different color here. J is at -3. So I'm going to take -3. And K is at 2. So I'm going to put 2 over here. Beautiful. So the absolute value of -3 minus 2 is -5. Absolute value of -5 is +5. Okay, now I need to find the length of LM, and because LM is vertical, I'm going to use the vertical ruler, which is the y-axis. So L is at 3, and M is at -2. Oh, 3 minus -2. What happens when I have minus a negative? They come together and become positive. So this is the absolute value of 5, and the absolute value of 5 is 5. Great. Are we done with this problem? Is that it? Can I move on? Oh, wait a minute. What did the question ask us to do? The question asked us to determine whether or not these segments are congruent. Well, what do you think? Segment JK is congruent to segment LM? Yes or no? Yes, because they're both 5 units long. And remember, line segments that have the same length are congruent. So, we will write yes, because they are both 5 units long. Ta-da! There you go. We can check our solution. Beautiful. Used the ruler postulate, and now we know that the segments are congruent because they have the same length. Yay. Happy day. Let's move on to the next important thing of today's video, the segment addition postulate. Now, this makes a lot of sense. When you read these words, you're like, what are you saying? That's confusing. But here's a question for you. Here is your house. This is your house. Beautiful. And here is the candy store. And that's a lollipop. A beautiful lollipop. And you want to walk from your house to the store to get some candy. It is 15 miles. Which is a long way to walk for a candy bar, but it's fine. It is 15 miles from your house to the candy store. You have already walked 10 miles. You're on your way walking to the candy store. You've already walked 10 miles there. How much farther do you have to walk? I think you said 5. And you'd be correct, because you've walked 10 miles, and you know you have to go 15, so 15 minus 10 is 5. This is the segment addition postulate. This candy bar walking question is the segment addition postulate. What it says is that if B is between A and C, which is just what they show right here, A is in between, or excuse me, B is between A and C, then AB plus BC equals AC. So what that means is this chunk, AB and BC together, make up the entire chunk. If you've walked 10 miles and you need to walk another 5 miles, these two added together need to equal 15. That's it. So the segment addition postulate, giving it a fancy name like that, can make it sound scary and intimidating, but really all it is if one point is between two other points, you can cut it into these two chunks, but those two chunks still make up the entire segment. That's it. That's all we're saying. Okay, so that is the segment addition postulate, but now let's see an example of it. So we're going to use the segment addition postulate. First problem asks us to find DF. I am going to draw on my diagram where DF is. Here's D, and here's F, so this is the segment I'm looking for. So, to find the whole segment, I know that this part is 23, and this part is 35. So to find the whole segment, I need to add 23 and 35 together. And that will give me 58. So I will say DF equals 58. I don't need to put the line above it because I'm talking about length. Beautiful. DF is 58. Okay. Next problem, new color. Find GH. So here's G, here's H. So this is the segment I'm looking for. This is just like the candy bar problem. 36 miles away. Your house is 36 miles away, and you've walked 21 miles. How many more miles do you need to walk to get to the candy store? Well, you need to go 36, and you've already walked 21. So 36 minus 21 is 15. 15. So GH, and I don't need the bar above it. I don't need the bar above it because I'm talking about segment length. GH is 15. There you go. That's it. So we can make sure that we were correct. DF is 58. GH is 15. Beautiful. Looks good to me. All right. Questions. Of course I can't take questions from you because this is a recorded video, but I specifically set aside one slide in every video to talk about the importance of questions. Questions are good. It means your brain is growing. It means that there's still more that you need to know in order to completely understand what we're talking about. So if you have questions, get those questions answered. There is nothing wrong with saying, hey teacher, I don't get this. Or, hey friend from math class, I don't get this. So please, ask a friend, ask your teacher. You can comment on this YouTube video. You can email me, you can email your teacher. Talk to people. They want to help you get your questions answered. Here are some practice problems. They look exactly like the examples that we have done today. So the first is exactly like example 2, and the rest of them are exactly like example 3. So plot the points and determine if they are congruent, and then use the segment addition postulate to find FH. So these questions might be different than the homework your teacher has assigned, so don't just do these problems and give them to your teacher. Make sure that you have checked with your teacher what the homework for this section is, and then do that homework. But these are here for you in case you'd like to try them. All right, and of course, we end every video with a launch. This launch says you are more than who you were. You can start over anytime, like today. The words I think are most important are you are more than who you were. Because were makes this in the past, right? As long as you are changing to become a better person, you are more than who you were. But you gotta put that old person in the past. So, who this applies to is everyone, because we've all done things that we're not proud of, right? We've all done bad things. We've said something mean, we've done something mean, something like that. And you can beat yourself up over, oh my gosh, I told Susie Smith in 3rd grade, I told her that her pigtails looked dumb, and she cried about it for 2 weeks, and everybody made fun of her, and I was a bully, and I feel really bad about that. You can beat yourself up about that for the rest of your life, or you can say, I was really mean to Susie, and it was awful that everybody picked on Susie. But I'm not going to do that again. I recognize that I was wrong. I've apologized to Susie, if you still are in contact with Susie, and I've done what I can to make it right. You are more than that. You're more than the bully you were in 3rd grade. You don't need to keep beating yourself up about doing bad things, because they're in the past. And you can start over anytime, like today. So if you're still bullying people because it makes you feel better about yourself, or because you just really don't like that person, you can stop that today. And you can start over today. You can go to Susie or whoever today and say, hey, I'm really sorry. I've been bullying you, and I've been embarrassed to say that was wrong, so I haven't said anything, but I'm saying something now, and I'm changing who I am now. You are more than the bully that you were. And you're even better because you were able to change the behavior instead of just staying in that cycle. And it's very easy to stay in a cycle of, I know I'm wrong, but I don't want to be embarrassed, so I'm just going to keep doing it. Like, no, break that cycle. Stop doing the bad things, and stop beating yourself up when you do bad things, because we all say things that, oh, whoops, I shouldn't have said that. So don't beat yourself up about it. You are more than who you were. You always will. So that is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.